So today we're going to be working on in-class activity. This is posted on Canvas. This in-class activity for chapter 3 is in-class activity 3A. So we're going to be working on this in class. I would actually recommend skipping number 1 and doing this one last. It's really easy. And it's based on an equation that we haven't really gone over very much yet. I added a little link so we could substitute for it, but pressure absolute. And it goes over this in the book, but I don't know if you've read it yet. It's pressure of the gauge, pressure not. So this is for question 1. Question 1 is pretty straightforward. It's just about using this equation and using like Boyle's law and ideal gas law. I'm not going to ask a question like this on the exam. There might be one on the homework, but it's just a little bit looking at pressure. I would actually start with number 2, 3, and 4 while you're here with me and you have time. So I would start on number 2. And then we'll go over number 2. If you feel like you're confident, go on number 3 and 4. And the solutions are posted. So if you're working faster than me, you can go ahead and just check yourself and then let me know if you have any questions. So start on number 2. We'll go over it in probably about 10 minutes, 15 minutes maybe. Cool. A book here? Okay. Either you brought tables, and maybe I see your book. Did you guys bring a book?
No.
Okay. I will let you use this one, and I'm going to go through. As a note to those online, you're going to need the tables in the back of your book. So the GCC and the steam tables. All right, I'm going to run upstairs to grab one of my other books for some of the people who are here right now. So I'll be right back, but just type anything into the chat if you have any questions. Okay. I will be right back, everybody. They're probably going to share maybe more. You can look it up on Google, but that'll be good. Generally, it's really short and it's easy.
See. For that, I got 0.0. Next one. The PR and the TR. So you take what she was giving and you divide it by the third piece. To get the and you can use that and that. Yeah. You can also look it up on your phone. I think you already have to. Your sister told me she had like a PDF version too. So you want it's hard to see and do that, yeah. But I mean, for these especially, just like as long as you kind of know what you're doing. I found these all. You're good?
Yeah, it was just
Yeah.
So very like PR equals.
I got corrected.
good.
And the same for temperature. General.
So that's what 900 volts. Yeah, but I think 0.9 megapascal fine.
Yeah.
Yeah, you
And for the first one, we had to bring 0.9 kilopascal. You leave it as negative
So you're good.
for the P.
How you doing? This is very similar to what I did on this.
But you don't bring it in kilopascal.
So,
Yeah.
yeah, for the ideal gas law, you do like, I mean, that's perfect.
I cannot read that.
Oh, I definitely feel like. I mean, like, it's kind of cool, but not really.
I didn't read it, but it's boring.
Yeah, I can definitely.
Oh.
Oh.
And then also, my eyes just went.
And
I cracked it.
Yeah.
I'm just
Very
saying.
kilo.
Well, you're looking at check it every year.
Yeah.
Good thing that I don't. Yeah, so for the first one, you PB equals an RT, but the B includes the math, so it's easy. And then the second one is where you have to use a generalized instability. So that's the one where we have to find pressure reduced by looking at the critical pressure. Yeah, these are, I know, that's why I like do some practice with them, that's like. I know. I don't know. Not bad. Struggling. Here's your general. All right, so here's your critical point resolution. Here's your general. There you go. I'm all good. You're gonna use this page first and then. Where did it go? Okay. Any questions for everyone? Everyone? Still working on.
I went. And then. Let's see. I was wondering why I got the same. And then you plug and chug with this equation. I got 0.8.
What did you get for your Z value?
0.89.
Okay, I got point, wait, 0.89. Okay, I got 0.91. And then remember that's your correction factor. So when you multiply that times by the ideal, that's where you get the grid. So you don't have to certify.
Ideal.
Number one, the absolute pressure.
Yeah.
Okay, so I'm gonna leave that one for now.
You can use this guy.
You're just gonna use pressure
Last
part. I don't think it's worth our time to do
So
here.
these are all different charts.
Well, they're not, I can't monitor that. Maybe when we're with. So, and you don't use any of those for either.
Oh, no, you put that down. Because that's part of the- you do that answer still. I'm jumping.
So for
C. Yeah.
Yeah, so for the second one, you're gonna, this is real similar to what I did on the say, where you first use the eigenvector, and then you will move up your critical point pressure, pressure reduce, reduce. Find it on the generalized facility chart, you find your Z value, you add a fraction. And then, yeah, so if you have your notes from Wednesday, it's fine. No, this is your PA, I think your notes and paper. Should be. Oh, no, my book is different because this is from when I took them. So it's much bigger. But you need your table 1 first to get your critical value. You good?
Yeah, that's stuck on 3.
Okay.
Or, temperature. Would it be the saturated?
Yeah. So anything in that liquid vapor, like region, is gonna be on that. So you really have to use what that pressure is.
Yeah.
Yeah.
And then for,
Mm-hmm.
You look first for pressure.
Yeah, that one.
And then you
Uh,
want my temperature.
And then that one.
So here.
So here's how you get your quality, and then you put it in the equation to get your enthalpy.
Okay,
And you'll also use it for specific volume.
how would I get,
This is
mass?
So there's another way to get
0.9.
quality using
and then
specific.
temperature here, so our actual volume,
So-
specific volume was this number.
I think we went over this one.
So our five pressure and then five temperature, and I can do it.
Yeah, and it's from the rearranging this equation. This is your specific volume on the average. There you go. Are you working on markers? Okay, so, so there's kind of a tricky part. So the way that you're gonna get quality is your mass of your gas over your mass flow. Yeah. That's their fault. Okay. So, the mass of your gas is not total is your quality, but you don't have your mass of gas on your mass flow. So we also have this equation where, our volume is equal to mass of our gas times specific volume of our gas plus mass of our fluid times specific volume of our fluid. So we can rearrange this to solve for this equation, or this becomes our specific volume on average minus specific volume of our fluid over specific volume of our gas minus specific volume of our fluid. That happens. So how do you get something they call like just in general, what is yes, and you're given volume. So this is but you can't work in meters if you're working. Yeah. You gotta convert it to meters. Yep, and then you divide it by kilograms, then you have this, which is two. So you don't have gas. Where would you find these?
Okay, I thought so.
Yep.
I wasn't sure. Thank you.
I thought it was, you look at this chart, because this is similar to what we did.
Are you guys still working on number 2?
We're on the three.
Are you guys still working on number 2? Okay, I'm gonna start going over it. All right, I'm gonna start going over number 2. So I'm gonna start going over number 2. Over number 2. All right, so let me change what I'm comparing.
You find 160, but it's in between 150 and 175, so I had stuck there for a second. But I added and divided both by 2 as a halfway point between those with 162.5. So if you were gonna go.
All right, so
But I don't know if that's working. I don't know if we did. Oh, maybe not. So that should give you temperature. It should give us temperature. Should give us temperature and it should give us VF and VQ. And I think we need all 3 of those to start.
okay, so hopefully everybody can see this. All right, for people online, let me know if you're not able to see this or if it looks weird or seems confusing. All right, so for this question, we're asked to determine the specific volume of, so we want to find the specific volume of refrigerant R134A.
Yes.
And we're told that our pressure is 0.9 megapascal, which is how many kilopascals? 900. 900. So this is 900. Good job, Emma, on line 2. Thank you, everybody in here. I pretty much always convert to kilopascals because you'll learn that you're going to be working in mega and kilopascals for these problems. So might as well just have those available. We're told that our temperature is 70 degrees Celsius, which we're also going to want to know in Kelvin. So how many degrees Kelvin is 70 degrees Celsius? So 374.1-ish Kelvin, because Kelvin is 273. Oh, wait.
Sorry.
That's not right. That's 373.1. Wait, that's not reading. Sorry, I'm reading the critical pressure. Golly, today is not my day. So 343.1 Kelvin. All right, so that's our Kelvin, that's our temperature. Sorry for my confusion. I'm not having a good day today. We're not told anything else in the problem, but we are asked to solve it using first the ideal gas law, second the GCC, and third just looking it up in our superheated vapor table, our steam tables. So for part A, we're going to use the ideal gas law. Ideal gas law, which is just PV equals nRT, but here we're going to use our V as our specific volume because it's going to include our moles term, our mass term that normally comes over here. So PV equals nRT. We can look up R in our table A1, I believe. And we are given T. We're given T and we're trying to solve for this specific volume. So now we're just going to plug and chug. Isolate the specific volume is RT over P. This is exactly like I was doing on Wednesday. Our R value, look up in table A1, go to the bottom. You'll see R134A. It's called tetra something. There's another name for it in the back of the book. I forget what it is right now. And the value is 0.08149 kilojoules kilogram Kelvin. There's an asterisk at the bottom that says that this is also related to another unit that includes the kilopascal, cubic meter. which, can somebody read that to me? Normally I have to look. Well, I can write it. All right, maybe not. What are these units, in other words? You guys know what I'm asking? All right, can I see the book? Yeah, table A1, and then at the bottom, so kilopascal, cubic meter, kilogram, Kelvin. All right, so these are also kilopascal, cubic meter, kilogram, Kelvin. So it's the same units, you can choose whichever ones work best for your problem. So that's our R value, and our T value is 343.1 Kelvin. And then we're going to be divided by 900 kilopascal. So I'm not going to choose these units, I'm going to choose these units. So here, kilopascal is going to cancel. My kelvins are going to cancel. And I'm left with cubic meter per kilogram, which are units of specific volume, which is what I want. So my specific volume based on the ideal gas law is 0.03106 cubic meter per kilogram. So here's my answer for part A. Thank you, Emma. All right. There's my part A. For part B, here's where I'm going to use my generalized compressibility chart. So I'm told my pressure is 900 kilograms. I'm told my temperature is 343.1 kilogram or Kelvin, and I'm trying to solve for my specific volume still. So this tells me that the values I'm going to need to look up in my to use on my generalized compressibility chart are going to be my reduced pressure and my reduced temperature. So my pressure reduced equation is going to be my pressure over my pressure critical. My temperature reduced equation is going to be my temperature over my temperature critical. And I'm looking up, I'm given my pressure and temperature. I'm going to be looking up my critical point pressure and my critical point temperature in table A1. So those are on the right-hand side of that table. It's the same table we looked at the R value in up here. And my critical point pressure for refrigerant R134A is going to be 4.059 megapascal. And I know my pressure here is 900 kilopascal or 0.9 megapascal. My critical point temperature is what I was trying to write earlier because I was getting confused my notes, 374.2 Kelvin. And I know my pressure of my system is 343.1 Kelvin. So now I know my pressure reduced is 0.22, I believe. And my temperature reduced is 0.92. All right, so now I want to try to figure out my V value so I can use my correction for my specific volume for my ideal gas law. Once I have my C value, I can use it to correct for this value. That says ideal, because this is from the ideal gas law. So that's my ideal specific volume. I'm going to use my generalized compressibility chart here. So I know that my pressure reduced is 0.22. So I'm going to be at 0.2. I'm going to go over 2. I'm at 0.22. And then I'm going to go up and find my temperature reduced line at 0.92. So my temperature reduced lines are here, right? T sub R. And then they kind of curve this way. So I have 0.9 and I have 0.95. So I'm going to use 0.9 and go up a little bit higher than 0.9, kind of just estimate a little bit. So I'm going to go up from 0.22 until I reach my 0.9 line, go up a little bit from there, come over not quite hit my 0.95 line, come over. I'm probably gonna be at about 0.9, 0.89, 0.91. I think the solution says 0.91. Based on this chart, I would probably say it's 0.89, 0.9. Doesn't really matter. So once again, I went to my pressure reviews that I calculated at 0.22. I'm gonna go up from there. I'm gonna hit my 0.9 line. I'm gonna not quite hit my 0.95 line, kind of go halfway between them. Come over here, probably about 0.89, 0.9. So that's my Z value. So this gives me a Z value of 0.9-ish. I think the solution says 9.1. It's fine. We're gonna do about. So from there, now I have my Z value. I can use this to correct for my ideal gas equation. So I know my specific volume based on an ideal gas is equal to 0.03106 cubic meter per kilogram. That's what was right up here. And I know that my actual specific volume based on my generalized compressibility chart is going to be equal to my correction value, my compressibility of Z times my specific volume ideal. So one of the equations that includes Z. And so this is just going to be 0.9 times 0.03106 cubic meter per kilogram. So this gives us 0.027954 cubic meter per kilogram. If this was a little bit higher or lower, that's fine. If you round off to 0.28, that's fine. That's okay. But here's our specific volume based on our generalized compressibility chart. All right. So now we're asked, in the third part, we're asked to compare these, or we're asked to find C, which is by using the measured properties table, using measured properties, properties table, also called steam tables. So for that, I'm going to go to the back of my book. I know that I'm going to be working in the R refrigerant or the R134A table. So here's my refrigerant, superheated refrigerant. Am I superheated, saturated liquid vapor, compressed liquid? For this one, we know that we're working with a gas. We know that we're working with a gaseous system. We know that we're at a high pressure and a high, we know we're at this certain pressure. We can assume for this problem we're using a superheated vapor. If you would like to, you can go to your table. All right, the table before for saturated liquid vapor, look at our pressure table here. At 0.9 megapascal, our saturation temperature is 35.53 degrees. We are much higher than the saturation temperature. We're double this temperature. So we're way above the saturation temperature. We're not even close to it at the same pressure. So that's kind of another good case that we're at a superheated vapor. So we're at a much higher temperature than the saturation temperature. We're going to go here and look up our 0.9 megapascal superheated vapor table, which is here, 0.9 megapascal. It also tells you here what the saturation temperature is. So if you think you have a gas, just go ahead and check if you're much above that saturation temperature. Then we can go to our temperature, which we know to be 70 degrees Celsius at this pressure over here. And we can look up the specific volume to be 0.2738. Wait. That's what? That's you, okay, great. The reason, so this is what I got from this book. The reason that I kind of hesitate, I think it's slightly different in the solution. It's the same exact step by step. We're gonna go to this 0.9 pressure, we're gonna go to 70 degrees, we're gonna come over, but this number is off by 0.0002. So probably just improved empirical evidence from the second edition of the textbook to this one. So anything around 0.0023 or 273, 274, that's fine. All right. So then we know that our specific volume based on empirical measured information is going to be about 0.0274. Okay, great, Emma. Yeah. So they must have just updated it from the second edition. The second edition, my husband used this when he took the class in Turkey in like, I don't know, 2005 or something. So it's definitely a bit dated. All right, so now we can see that our best method of approximating is not using the ideal gas law, but using our generalized compressibility charts, or even better, just looking up what the value actually is. Okay, so I'd like for you to get started on number 3. One thing to know about number 3 that I went over kind of quickly, but I didn't do it enough to leave you on your own. So this is for problem number 3. So we have quality, which is going to be the mass of our gas over the mass total. But for this problem, we're not given information about either of these. So we have to kind of figure out a way to find quality in another way. And one thing that we can remember is our volume total is going to be equal to our mass of our fluid times our specific volume of our fluid, plus the mass of our gas times the specific volume of our gas. And also our specific volume of our system is going to be equal to our total volume over our mass total, which is also our total volume over the mass of our fluid plus the mass of our gas. So you guys are probably already seeing that you can kind of rearrange these based on volume to get quality, which you can. So we can use this by getting our specific volume on average, or the specific volume of our system minus the specific volume of our fluid or liquid over the specific volume of our gas minus the specific volume of our fluid. So here's another way of getting quality. All right, so I want everybody to work on number 3, and I'll go over that in probably about 15 minutes. All right, so we're working on number 3. Yeah, you can use whichever one. Yeah, okay. So this one is like typically if you're given temperature, but you don't know what your pressure is, and the other ones are for if you're
I
given.
did that one out.
Yeah. Oh, you were asking if you can use mine.
No, I was just asking if I can use that chart. She has it.
Oh, great, yeah. I'm pretty sure. Yeah,
And then we should do,
so you're told, okay, well, so most of the time you can figure that out by looking at the table, but there's an hint in this question that tells you what you're doing. So what is the second thing?
quality is what I'm saying.
Quality, quality.
Oh, okay. So then we need, our final and I believe.
Right. So your whole system is gonna be on that factor system.
And then does it have a regular beads as well, or just the BG?
You just have to make sure you're in the right table. And
So we know that it's exactly.
Right, yeah.
And so we got an ample fee right in the draft.
But you can't just look up anything except for temperature, because your whole system's gonna be at temperature, but your system's gonna be part liquid, part vapor. You have enthalpy of your vapor and enthalpy of
One
what?
what?
And you need to include that equation y equals y on x or y.
We know that we're gonna sure.
No, no, it's the one, where you're like including quality. So, yeah, that one.
5.9.
And that one you can apply for specific volume and
Okay.
enthalpy. So you have to, first you have to solve for
And I.
quality, and then you can start solving for density.
So that's just for all.
Yeah.
And what was the-
So you can
I'm
find
not saying you want me to read that.
quality this way, this is the this way, but you don't have any information on the mass of your gas. You only have 4 kilograms of mass total. So how are we gonna figure out the mass of your gas? So you have to use another one, which is specific volume. So that's just like kind of to give you the quality, and then you have to use that y equals y plus x times y of t in order to get your input.
Where do you find the regular bead that's on top?
So what is the definition of specific volume?
Oh, okay, so it's, yeah.
Volume of mass, and you're given volume, you're given mass. So you can find this.
Oh, thank you.
I will be right back.
Yeah, temperature was the first one, was the 111.
All right, so any questions from anyone online? Any questions over here?
Yeah, surprised, not quite yet. For that case, that's. So, so you have, yeah.
Yes. So that's just your volume, but your temperature here, you're gonna use your Q.
And then it's
It's
meters,
not an ideal.
and everything else in here is meters cubed.
It's not even a gap. Part
So
of
then you
it.
have to divide it by 1,000.
So that's where you have to use that pressure to do. Paper table to like, whoa,
Have any other.
for our 134A. And do you know temperature or do you know pressure? Right, so you're gonna use the pressure table. Yeah, so you're on the right table. You just have to figure out what, 160 megapascal Yep. You okay? Thank you. If you want to stay and work on practice problems, you're welcome to.
Yeah.
We're working on number 3. I think Justin's already done number 2 and number 3, so he can help you. Yeah, right. Then it would be way too hard. Are you guys, any questions?
Did I do this right? I divided it by 1,000. Right?
Yeah, so you need to divide by 1,000 per cubic meters, so it's 8 times 10 to the negative 2 cubic meters, or 0.008. Oh, I did that at the beginning, you did it at the end. That should be fine.
Yeah, I did, yeah. So it's 0.00.
For part D, no.
First of all, that's 120. For X.
Oh, yeah, it's just 2, yeah.
Thank you.
No. You have to convert 80 liters to cubic meters.
The reason why is because if you look at the chart, it has it at the very top.
Yeah. Pretty much we always work in kilopascal, megapascal, cubic liters, and Celsius per Kelvin. Like if you have anything else besides those, it's like assuming. All right, how's it going?
No.
Oh, no, okay. So,
Remember Wednesday, Friday?
yeah, today's rough.
Specific on, this is gonna be 20.
Yeah, but you gotta convert to cubic meters because everything in here is like. So this is 2 cubic meters. And so then you have your basic specific volume. You can look up your specific volume of your gas. The whole thing is the same. So you're all you're gonna. So G is gas, F is fluid, but I say vapor and liquid because it looks first. So it's fluid and liquid, gas. And vapor.
Oh, yeah, so then, top is gonna be that 2. There's cubic meters per. They're both gonna be minus the fluid, the liquid.
These are, which is what?
I finally.
Yes, but.
Excuse me, sorry.
Yeah, that's right, except for my mislabio, it's 2 times 10 to the minus 2 cubic meters per kilogram, so it is at 0.002 minus 0.0007. So it's, but yeah, and then,
So. For the top, 0.002 minus, and then the bottom is gonna be the vapor. 1, 2, 3, 4, 8.
Yeah.
Minus.
and then that gives you a unitless value for your volume. That's going to be 0.
With it.
So now remember that Y equation. Okay, so well, part B is just like what is the quality? There for use on G. For C, you have your enthalpy of your system, the enthalpy of your gas, plus the enthalpy plus your quality times the enthalpy of your gas vapor or your gas liquid, your liquid vapor. Which, if you remember, the equation for that is the it's the enthalpy of your gas minus the enthalpy of your fluid, which are one bigger. The enthalpy of
So I'm sorry, I lost that, because this is gonna be unitless value.
Yeah,
right? And what is that?
that's
That's the quality. Yes.
yeah, so quality tells you how much of your system is big. And then it also is related to, well, okay, so how much of your system is vapor? That's what it's called. So then for your enthalpy, for your specific volume, or your entropy, everything, those are all going to be, you have a vapor and you have a liquid. Those are your values. And so this tells you, okay, it's like 0.157, so like 15% of your system roughly is liquid. So now you have to include that percentage in all of these like values. So you have to find some value between your enthalpy of your fluid and your enthalpy of your gas. And so you use that using that y equals y plus x times y of t.
What is Y?
Y is just like a basic variable. So your y can be enthalpy, which is H, or it can be specific volume, or it can be entropy of ash. It's just a generic equation.
Yes.
So once you have your quality, you just have to look up your enthalpy term for your vapor, your G, and then for your liquid, your F.
Without doing that, you said it was what?
0.157 is your X value for quality.
So that means that the system is roughly 15.7% vapor.
Yeah, we don't really ever talk about it in percent, but your quality is 15 or 0.15. So like, if you have 100 kilograms, 50 of those are vapor. The other 85 are liquid. So for enthalpy now for the next one, you're asked like, what is enthalpy? So enthalpy is going to be H, which becomes your first line. H equals H of F plus X times H sub FG. But you don't have an FG value in here. Oh, wait, you do for enthalpy. You don't. Those are my ones. So for this one, you can really that foundation.
So we just look up the entropy, it's just the HF3.
Well, it's H sub F plus X times H.
I divided by 1,000.
H sub F we have.
Yeah, well, you did it all.
That's, yeah.
It's the R2 and the P, right? And
No.
so P we got.
For volume, you're gonna be reusing like these equations.
Okay.
You get R.
Specific for your total volume of your vapor. So this is your volume of your vapor. The specific volume of your vapor times the mass of your vapor. And you know this. So you can get your mass of your vapor because you know quality times your total mass is equal to the mass of your vapor. Your total mass is given at 4 kilograms, you solve for your quality. And that gives you your mass of your vapor. Your mass of your vapor times your specific volume of your vapor gives you your total volume. Okay, I'm gonna answer the question. Yeah. Okay. Sorry, everybody, I'm here to answer questions. All right, so for part A, you do not use the ideal gas law. It is even easier. You just look it up in a steam table. So steam table for part A. I'm gonna go over this in just a few minutes, but this is not a gas, and further, it is definitely not an ideal gas. There's a hint in part B where it asks for quality. Quality always equals saturated, liquid, vapor. The only thing that has quality ever is a saturated liquid vapor. So you're gonna look up table A12, which is your saturated liquid vapor table for R134A. And you're gonna use the pressure table because you're given pressure. So you're not gonna use ideal gas law. It is not a gas and it's definitely not an ideal gas. Okay, so I'm gonna go over in just a few minutes, maybe see if you can work it with that new information. And then I will go over it. All right, any burning questions? No. Okay. Great. Okay. I always feel that way. How's it going?
Good. I'm I got the pages right.
Yeah.
The first one, saturated liquid vapor. Down to second.
She gave us several.
Yeah, and the last one. How do I find there?
So there's no.
So, yes.
But you can assume that if we did the compressed liquid, there's absolutely no vapor. You can use the stuff, but they're charged.
So it would just be at either one of these temperatures. Or pressure. Temperature, pressure.
So your temperature is lower than your saturation temperature, and
Yeah.
you know it's a compressed liquid, so you can just look up. Your U is approximately your U sub F for table A4, which is your water temperature table. And so you have to do the pressure, right? You're only going to
Oh, for this one?
for the last one, you're going to 500 kilopascal, yeah, right? So you can just look up that 500.
That's all right. This is empathy.
And then you, obviously, you, well, is there a quality? Or it's just-
Go ahead. It's.
Oh, wait, no.
Yeah.
It's vapor.
Oh, the example is weird now.
So you would be like 639. But yeah,
Is that at pressure?
this is one given temperature.
Okay, so you, I guess look at it. Okay, yes, compressed liquid water at fairly low pressure, such as 500 kilopascal, will not enter and thermal energy very close to the value for saturated liquid at the same. I don't think I want to. All right. So I'm gonna start going over number 3 unless anybody would really like a few more minutes. I'm gonna start going over number 3 unless anybody would really like a few more minutes. All right.
Yeah, sorry.
All right. So for this problem, we are told that we have an 80-liter vessel. So our volume is 80 liters, which I know right off the bat that I'm going to convert into cubic meters. Typically for this chapter, we're always going to be working in megapascal and kilopascal, degrees Celsius and Kelvin, and cubic meters. So I pretty much know I should have conversions for all of these right when I start a problem. It's easier for me to do them up front. So 80 liters to cubic meters, we're going to divide by 1,000. So here's where we have 0.008 cubic meters, or 8 times 10 to the negative 2 cubic meters. Right. Not right. I was thinking, why aren't those the same thing? Like 0. So dividing by 1,000. Okay, so in the solution, what we did next was to automatically, we have a mass of 4 kilograms. So we know volume and we know mass, so we automatically just calculated the specific mass of the system, which is 0.08 cubic meters per 4 kilograms. which is 0.02 cubic meters per kilogram. All right. So the next thing that we want to do is determine, is this a compressed liquid, saturated liquid vapor, saturated vapor, or superheated vapor. So sometimes next week, we're going to be determining this based on looking at the tables and comparing values. But for this question, it's really easy because we are asked to determine quality, and quality only ever exists for saturated liquid vapors. Saturated is what portion of your liquid and vapor is vapor. So it only ever occurs when we have liquid and vapor. So there's a hint in the question that this is saturated liquid vapor. So this means we're going to be using table 8. So table A4 is our, I'm sorry, it's not table A4, that's for water, it's table A12. Because we're using refrigerant R134A. A4 would be if it's water. I'm making a lot of mistakes today. Hopefully I'm better on Monday, I apologize. All right, so we have our volume, we have our mass. So this time, unlike some of the other problems, we're not given pressure or temperature. So we got to kind of approach it a little different. The first question here, we're asked to find temperature. And I know several people use the ideal gas law because it's what we've done before, but it's even easier, luckily, because we know what table we're going to use and we know a pressure. Because we are also told pressure, I don't hear that down. We have 160 kilopascal is our pressure. So we know what table we're going to use and we know pressure. And if we know what table we're going to use and we have pressure or temperature, we can find the line that gives us things like specific volume, enthalpy, entropy, internal energy. So if we want to find temperature, all we have to do is go to table A12 at pressure equals 160 kilopascal. And look up our values for our saturated pressure. Our saturated temperature. So in this mixture region, in this liquid vapor region, the temperature of the system is always going to be equal to the saturation temperature. This is where the reading and the definition will help you kind of understand this concept. But the water here is turning into a gas. It is vaporizing and kind of sometimes condensing a little bit, but always your temperature of this mixed region, this system, is going to be your saturation temperature. So your T-sat at 160 kilopascal is going to be negative 15.6 degrees Celsius. Okay. So then for part B, we're asked to solve for quality, which is why we knew it was a saturated liquid vapor. Quality is the amount of our total liquid vapor that is vapor. So how much of our system is actually vapor? Typically, we're going to use that equation of how much vapor, M sub G, is there out of our total mass. But for this one, we're given our total mass, but we're not given X and we're not given our M sub G. So we can't really solve for this equation. So we need to use another equation, which is what I presented at the beginning, where we have our specific volume minus the specific volume of our fluid, our liquid, minus the specific volume of our gas, minus the specific volume of our fluid. We already have our specific volume of our system because specific volume is just volume over mass. And we know what table we're going to use at what temperature and pressure, so we can just look these up from our table. So our V sub F, our specific volume of our fluid at this pressure, is going to be about 0.0007 cubic meter per kilogram.
How did you get that? Because we put it on 150 and 175. So we went 150 because 160 was closer. We were. Never mind.
Okay. Here, I'll still explain this in case part. All right. So here's our table for saturated refrigerant 134A. It's our liquid vapor table. We're looking at pressure. So this pressure is in millipascal. So this is 0.16. So right here. Here's our saturated temperature. And here is our saturated liquid specific volume. So 0.0007435. And then our saturated vapor V sub G is 0.1229. So these are slightly different in the version 9 textbook. These are updated. So our V sub S or our V sub G S, our specific volume of our vapor of our gas is about 0.124 cubic meter per kilogram. From the table there. So now we have everything that we need to solve this. So if we plug this in, we get 0.0 from a pure specific volume, so 0.02 minus 0.0007 over 0.124 minus 0.007. So this is roughly 0.16 as our quality. So the solution says 0.157. It doesn't matter, you can round 0.16. Yes.
When you look at the table, how do you know before you get the answer that's 0.16?
What do you mean?
Like, before we found like it's 0.16, we looked at the table and the pressure was 0.16, but how did we know?
Oh, that's just a coincidence. So this pressure is pressure in millipascal. So I'm sorry, I should have gone over that a little slower. In our problem statement, we're told that it's at 160 kilopascal, which is equal to 0.16 megapascal. It's just a coincidence that it's also the same as our quality. Yeah, sorry. Okay. So now we have quality. So that's part B, which means that roughly, 16%-ish of our system is going to be this vapor. So now we want to solve for enthalpy, which is our heat content, enthalpy, which is H, specific enthalpy. And when we look up enthalpy, we can look up enthalpy in the table, the same table, table A12. We can look up our enthalpy values. Here we have our enthalpy of our liquid, our enthalpy of our gas, and for enthalpy, we're also given our enthalpy of our liquid vapor region. So these are going to be, the enthalpy of our liquid is going to be 31.13 kilojoules per kilogram at 0.16 megapascal. The enthalpy of our gas is going to be 241.14 kilojoules per kilogram. And the enthalpy of our liquid vapor is going to be did somebody look it up? My book is dated. It says 208.18. Yeah. 208.18, but I think my values are a little bit off. Yeah, this is I just miscopied this. All right, well, so now we have these values. How are we going to get our enthalpy of our system? So here's where we're using that equation where our H, this is that generic equation y equals y sub f plus x y ft. And so if we're doing this with enthalpy, we can use enthalpy is equal to enthalpy of our liquid plus quality times enthalpy of our liquid vapor. We have quality from part B. We have our enthalpy values here because we looked them up. So now we can just plug and chug. So 31.13 plus 0.16 times 208.18 kilojoules per kilogram. Kilojoules per kilogram. Sorry, I'm dying like. As a reminder, you can also do for your H F sub G, you can do H sub G minus H sub F. So H F sub G is equal to H G minus H F. So you could have always calculated that yourself, or if you need to, you can leave it kind of pulled apart depending on what you're trying to solve for. The way that the solution is done in the solution manual, the professor who taught this a few years ago actually pulled out this quality term and worked it slightly differently, but it's the same solution, it's the same approach. He just kind of pulled out this 1 minus x for the quality. We factored out x. All right. So plugging this in, I think we get 64.4 kilojoules per kilogram as our enthalpy. All right. So the last part is to determine the volume occupied by the vapor. So for part D, we want volume occupied by vapor. So we know that the volume of our vapor is going to be the mass of our vapor times the specific volume of our vapor. That's the definition of specific volume. And we know that our quality is going to be the mass of our vapor over the mass total, which is also the mass of our vapor over the mass of our fluid plus the mass of our gas. So we can rearrange this. The mass of our gas is equal to quality times the mass of our fluid plus the mass of our gas. Or just mass of our gas is equal to X times the mass total. Either way. So then if we have our volume occupied by gas is equal to X MT times the specific volume of our gas. Well, we've already looked at the specific volume of our gas from a table. Now we have quality and we have our mass total. Mass total is given in the problem statement, quality we solved for. So now we can just do 0.16 as our quality times 4 kilograms, which is given in the problem statement, times our specific volume of our gas, which we looked up in table 812, which is 12.36 times 10 to the negative 2 cubic meter per kilogram, or 0.1236, 0.124. So then this equals, got carried away. This equals 0.0776 cubic meters. And if we want to convert back to liters, this is going to be 77.6 liters. Is the volume occupied by our vapor. All right, so we're almost done with class. I want you to try to complete number 4 by yourself. One thing I will tell you about number 4, if you have a compressed liquid, if you have a compressed liquid, use your saturated liquid vapor table, but you're only going to use stuff with a subscript of F. And so it's entirely liquid. Your compressed liquid has no vapor component at all, but we don't have a separate table for compressed liquid like you do for saturated vapor. And your compressed liquid is going to be, you're going to use looking up based on temperature. So use your temperature table, not your pressure table, because in general, at these relatively low pressures, your enthalpy, internal energy, enthalpy, everything are going to be the same as a saturated liquid at the same temperature, which is why we use temperature. So number 4 should be pretty easy. It's just more practice using the table. So please work on number 4. Maybe we'll work on it a little bit next week, but please do that on your own. And are there any questions from anyone?
The X part of it, do you use the same equation you gave us for question 3?
If you need to. So it depends on if you're given. So the question was for quality, are we using, which equation are we using? Do we need to use the one that was given to me during class? And quality is only relevant for saturated liquid vapor. And that quality this is also going to be the same. You could also do this for internal energy, specific internal energy. So that might be helpful as well. It's just the same exact concept. All right, any questions from anyone? All right, so please do number 4 on your own. I think it'll be a similar one on the homework than the homework, so you'll get to practice it there. But have a great weekend. I know I really need it, so enjoy.
Have a good weekend.
Thank you. Oh yeah, sorry. Oh yeah.
I'll see you Wednesday.
Yeah, both.
1:30.
Thanks, Professor. Thank you.
That's what it is. Like, how do you find the, what's specific wrong with
Good. But I put 10 to the minus 2
Yeah. Oh, because it's.
because I just did 12. Yeah.
Oh, yeah.
Thank you.
You just left. What? You just left. No, he's drove with me.
Have a great one.